Welcome to Healthcare Workflow Process Improvement, Process Mapping, Lecture E, Entity Relationship Diagrams. This lecture includes the background and development of entity relationship diagrams, ERDs, the process aspects that are covered by ERDs, how ERDs are used, the symbol set, and notation conventions. This lecture also covers how to read an ERD rather than how to create one. The objective for this lecture is to read and interpret an entity relationship diagram in crow's foot notation. Topics covered in this lecture should prepare you to understand the background of how entity relationship diagrams, ERDs, are used and maintained, the symbol set used in producing ERDs, and process aspects covered by them. Understand the notation conventions and be able to read, not create, a simple ERD. Entity relationship diagrams are also called ER diagrams and ERDs. The concept for ERDs was introduced in the 1976 paper by Peter Chen. Chen, 1976, just 7 years after E.F. Codd, 1969, published his seminal work defining the relational model of data. Chen's notation provided a way to graphically show relationships between data values. Thus, it is best described as a data model. More specifically, a logical data model, because it describes how the data are related, not the physical locations of the data values within computer memory or how they are stored in a database. Logical data models, referred to as just data models for the rest of the presentation, are used to represent or document the data that are needed, collected, stored, or otherwise used for some business need or needs. A data model is a description of the data rather than how the data are used or how the data move through a system. Thus, such descriptions are called static models or models of information content. Descriptions of how data moves through a system would be called dynamic or behavioral data models. ERDs, and for that matter, static data models in general, were not designed to, and in fact cannot, model process steps, step sequence, or flow control. Static data models convey just the data. ERDs are used in projects where the data content for a system needs to be documented. As a workflow analyst, you will most likely not be creating ERDs. However, you may run into them as either documentation provided by a prospective vendor that documents the data in their system stores, or documentation that a healthcare facility has for an existing system. ERDs are based on the relational data model. Codd, 1969. Briefly, the relational data model describes fundamental ways in which data values may be related to each other, and as such, guides the design of a relational database in such a way as to keep those relationships intact. Full appreciation of the information conveyed on an ERD requires knowledge of the relational data model. Importantly, this course does not require knowledge of the relational data model or of databases built based on the relational model. Most community colleges and universities have courses on relational databases and relational database management that cover the relational data model in depth. Lecture E covers reading and interpreting ERDs, not how to create them. ERDs are similar to Unified Modeling Language, UML, class diagrams. They are both static data models. ERDs predate the development of the UML standard by over a decade, and the influence of ERD notation and methodology on UML class diagrams is quite visible. Although class diagrams represent additional relationships that ERDs do not, they both can represent multiple levels of abstraction and the incorporation of hierarchy where the lower-level classes inherit attributes from higher-level classes. This is referred to as inheritance. Class diagrams can be used to show individual pieces of data and their attributes and relationships. If just this data content is needed, ERDs are equivalent to UML class diagrams. Class diagrams are covered in a separate lecture. To summarize the important points so far, ERDs are used to specify or document static content, i.e., data that are or are to be stored in a data system. As such, ERDs are often used as the starting point in the design of relational databases. ERDs are included in this unit because data and information are used, collected, and stored in many work processes, especially those in information-intensive settings such as healthcare. Data are a part of healthcare workflow and need to be considered and understood along with the workflow steps. Thus, the Workflow Process Improvement Specialist may encounter ERDs. Further, the Workflow Process Improvement Specialist will need to know when data are important to a clinical workflow and when to take these data into account as part of a process redesign. Several notations exist for drawing ERDs. The most common is Barker, or crow's foot notation. Crow's foot notation is favored over the original Chen style of ERD modeling because of its readability and more efficient use of drawing space. Data model diagrams provided by software vendors often use crow's foot notation. We will cover only crow's foot notation in this lecture. We collect and store data about things in the real world. When these data values have meaning, i.e., definition, context, such as what the value is about, when it was collected, etc., we call the data information. Often the meaning is assumed and the word data is used interchangeably with the word information. Nonetheless, data models including ERDs represent three things. 1. Entities or things about which we collect data. For example, cars, people, organizations. 2. Relationships between the data values. For example, a person can have no cars, one car, or many cars. And 3. Attributes, or the data that we collect about the entities. For example, we may be interested in the make and model of a car, or the name and address about a person. Make, model, name, and address are considered attributes of the entities, cars, and people. An ERD looks like this. There is only one type of ER diagram, a data model. The ERD in the example describes the data that might be used to manage courses and student registration. A data system for managing student course registration would need data about courses, instructors, course sections, course seats, and students. These are entities. The course registration management process might require course name, number, and credit hours. These are attributes. The course registration management process might also require instructor name, number, and department. These are also attributes. In ERD notation, the entity name appears in the top of the box. The attributes are listed in the box below the name. The lines connecting the boxes convey information about the relationships between the data. These relationships may be a model of reality, or may document constraints or business rules required by a process or data system. The statement, "Every student must have a student ID," is one such constraint that may or may not reflect reality. In ERD crow's foot notation, an entity is represented by a two-part box, i.e., the top section that holds the entity name and the bottom section where the attributes are listed. An entity has a name, attributes, and an identifier that uniquely identifies instances of the entity. Unique identifiers are similar to Social Security numbers. Each number is distinct and is assigned to one and only one person. Thus, if we had a list of 12 Social Security numbers, we could be assured that the list represented 12 different people. An attribute that acts as the unique identifier is added to the entity or is selected from the attributes that meet the all-important criteria of being capable of serving as a unique identifier. Sometimes on an ERD, you may see boxes that have an entity name but no attributes. This is done on draft programs as a placeholder to show that information about the entity is needed but has not yet been specified. For the course entity shown on the slide, a database would store the course name, number, and credit hours. Importantly, the course entity box signifies that the database holds data values about courses. Each actual course for which data exists is called an instance of the course entity. If there were a person entity, you and I would be considered instances because we are real and exist. The generic entity, person, or course on the slide are called universals because they represent the existence of instances. Relationships between instances of two entities are represented by a line. Relationships have a name, which is a verb. ERDs only show a few types of relationships. UML class diagrams are capable of representing additional types of relationships. The types of relationships represented are 1. The existence of a relationship denoted by the presence of a line between two entities, and 2. The maximum and minimum number of times an instance, actual occurrence, in one entity can be associated with instances in an entity with which it has a relationship. These maximum and minimum numbers are called cardinality and modality, respectively. These are the only types of relationships represented in data models. Cardinality and modality work together to define the relationship. Cardinality indicates the maximum number of times an instance in one entity can be associated with instances in the related entity. Modality indicates the minimum number of times an instance in one entity can be associated with an instance in the related entity. Thus, modality is also called participation because it denotes whether or not an instance of an entity must participate in the relationship. Cardinality and modality are both shown on the relationship line by symbols. We will go over each of the symbols and how to interpret them. Cardinality indicates the maximum number of times an instance of one entity can be associated with instances in the related entity. Cardinality can have the values of 1 or many. No more detail than that. It is either 1 or more than 1. On the relationship line, the cardinality is the closest to the entity box. The cardinality symbol in the diagram on the slide is in the red circle. Cardinality is indicated on both ends of the relationship line, so there is a left-to-right cardinality and a right-to-left cardinality. Modality indicates the minimum number of times an instance in one entity can be associated with an instance in the related entity. Modality can have the values of 0 or 1. 2 or 3 are not allowed. The modality symbol is located next to the cardinality symbol, on the inside of, i.e., not next to the entity box. A modality of 1 is denoted by a straight vertical line, and a modality of 0 is denoted by a circle. Like cardinality, modality is indicated at both ends of the relationship. Once you have the three symbols, 0 circle, 1 vertical line, and many crow's foot committed to memory, reading them is easy. Let's go over them, starting from the top of the slide. Modality 0 and cardinality of many means that instances of the entity on the left of the relation can have or be associated with from 0 to many instances of the entity on the right. Modality 1 and cardinality many similarly means that instances of the entity on the left of the relation can have or be associated with from 1 to many instances of the entity on the right. Modality 1 and cardinality 1 means that instances of the entity on the left of the relation can have or be associated with 1 and only 1 instance of the entity on the right. Modality of 0 and cardinality of 1 means that instances of the entity on the left of the relation can have or be associated with from 0 to 1 instances of the entity on the right. Remember, cardinality and modality specify a range. On an ERD, modality and cardinality look like the examples in the slide. Remember that these are shown on both sides of a relationship. Thus, there is a left to right and a right to left reading direction. Pause the slides and read through each of the examples. The seat fill student example shows left to right. A seat is filled by exactly 1 student. Right to left. A student fills exactly 1 seat. The student has transcript example shows left to right. A student has 1 or more transcripts. Right to left. A transcript has 1 student. The student registers for course example shows left to right. A student registers for one or more courses. Right to left, a course is registered by one or more students. The instructor teaches course example shows. Left to right, an instructor teaches 0 to many courses. Right to left, a course is taught by exactly one instructor. Reading cardinality and modality, seat to student to transcript, student to course, instructor to course. Source, adapted with permission from Burnett. When people talk about relationships between entities, they use phrases like one-to-one, many-to-one, or many-to-many. When people refer to the relationships in this way, they are calling out the cardinality, maximum number allowed, only, i.e., not mentioning modality, the minimum. Pause the slide and read through the relationships for each example. Note that cardinality is used in both directions. In these examples, the digit 1 denotes one. The letter M denotes many. The seat fills student example shows left to right, 1-to-1, 1-1. Right to left, 1-to-1, 1-1. The student has transcript example shows left to right, 1-to-many, 1M. Right to left, many to one, M1. The student registers for course example shows left to right, many to many, MM. Right to left, many to many, MM. The instructor teaches course example shows left to right, one to many, 1M. Right to left, many to one, M1. Because the X to X way of referring to relationships does not account for the modality, there are 4 different ways that a many-to-one relationship can occur based on different combinations of modality. The 4 varieties of a many-to-one relationship are shown on the slide. One through many notation on one side of a relationship and a one and only one. 0 through many notation on one side of a relationship and a one and only one. 1 through many notation on one side of a relationship and a 0 or 1 notation on the other, and 0 through many notation on one side of a relationship and a 0 or 1 notation on the other. Similarly, because the X to X way of referring to relationships does not account for the modality, there are 3 different ways that many-to-many relationships can occur based on different combinations of modality. The 3 varieties of many-to-many relationships are shown on the slide. A 0 through many on both sides of a relationship, a 1 through many on both sides of a relationship, and a 0 through many on one side and a 1 through many on the other. And finally, because the X to X way of referring to relationships does not account for the modality, there are 2 different ways that a one-to-one relationship can occur based on different combinations of modality. The 2 varieties of a one-to-one relationship are shown on the slide. A 1 and only 1 notation on one side of a relationship and a 0 or 1 on the other, and a 1 and only 1 notation on both sides. We will use this ERD example in the following slides. A doctor can be scheduled for many appointments, but may not have any scheduled at all. Each appointment is scheduled with exactly one doctor. A patient can schedule 1 or more appointments. One appointment is scheduled with exactly 1 patient. An appointment must generate exactly 1 bill. A bill is generated by only 1 appointment. 1 payment is applied to exactly 1 bill, and 1 bill can be paid off over time by several payments. A bill can be outstanding, having nothing yet paid on it at all. 1 patient can make many payments, but a single payment is made by only 1 patient. Some patients are insured by an insurance company. If they are insured, they can only carry insurance with 1 company. An insurance company can have many patients carry their policies. For patients that carry insurance, the insurance company will make payments. Each single payment is made by exactly 1 insurance company. We will go through sentence by sentence on the next several slides and trace through the associated ERD. A data analyst will meet with clients who are subject matter experts and work with them to elicit the information needed to model their data needs. This paragraph is a very simplified example because each data need is clear and completely stated. Thus, it does not represent the information that an analyst encounters in a real-world setting. In the pink box on the slide, you see that a doctor can be scheduled for many appointments or may not have any scheduled at all, i.e., a doctor can have 0 to many appointments scheduled. Each appointment is scheduled with exactly one doctor, i.e., an appointment can have only one doctor associated with it. In the blue box on the slide, you see that a patient can schedule one or more appointments. One appointment is scheduled with exactly one patient. In the orange box on the slide, you see that an appointment must generate exactly one bill, and a bill is generated by only one appointment. In the yellow box on the slide, you see that one payment is applied to exactly one bill, and one bill can be paid off over time by several payments. A bill can be outstanding and have nothing yet paid on it at all. In the orange box on the slide, you see that an appointment must generate exactly one bill, and a bill is generated by only one appointment. In the yellow box on the slide, you see that one payment is applied to exactly one bill, and one bill can be paid off over time by several payments. A bill can be outstanding and have nothing yet paid on it at all. In the green box, one patient can make many payments, but a single payment is made by only one patient. In the purple box, some patients are insured by an insurance company. If they are insured, they can carry insurance with only one company. An insurance company can have many patients carry their policies. In the yellow box, for patients that carry insurance, the insurance company will make payments. Each single payment is made by exactly one insurance company. Crow's foot notation is one of several ways to represent static data content. Because of widespread use, it has become a de facto standard. Importantly, the notation encompasses key information about static content that is needed to specify a database. Most likely for this reason, the concepts represented in this notation have been carried forward and built upon in UML class diagrams. This concludes Lecture E, Process Mapping Entity Relationship Diagrams. As a workflow process improvement specialist, you may encounter ERDs and need to get information from them about data that are used or generated in a process. Thus, being able to recognize an ERD and read pertinent information from one is important. In summary, we covered the background of ERDs and process aspects covered by them, i.e. static content. We introduced the symbols and notation used in ERDs and worked through several examples reading a simple ERD. You should now be able to recognize an ERD and be able to read and interpret the diagram. For more exposure to ERDs and the relational data model, we suggest a course in relational databases.